All right.
Happy New Year.
Happy New Year. Happy New Year. So, chapter 6, trigonometric identities. Pardon? Whose?
Wait, did we sing her?
We did not.
Happy birthday to you. Happy birthday to you. Happy birthday to you. That's a song. It's Peter Lahita. Okay. Happy birthday to you.
That kind of went sideways, but yeah.
Yeah. You forgot my name. I got the same year, and everybody's like, no, I was exactly.
Okay. Chapter 6. So, after this chapter will be our next unit exam, chapters 4, 5, and 6 on trigonometry. This chapter deals mostly with what are known as trigonometric identities. So we're going to verify a trig identity numerically and graphically. We'll look at reciprocal quotient Pythagorean identities. We'll look at determining the non-permissive values of trig identities, and then talk about the difference between a trig expression and a trig identity or equation. Okay? So, on the next page, the equation sine x equals cos x tan x is an example of a trig identity. If we look on the right side, a trig identity is a trig equation that is true for all permissible values of the variable in the expression on both sides of the equation. So a trig identity is a relationship between two different trig expressions that are equal to each other. Both sides of the equation have the same value for all permissible values of x. In other words, when the expressions on either side of the equal sign are evaluated for any permissible value, the resulting values are equal. Trig identities can be verified both numerically and graphically. We're already familiar with a couple identities, trig identities, and those were our reciprocal identities, that cosecant is 1 over sine x. That is an example of a trig identity. Secant is equal to 1 over cosine, and cotan is equal to 1 over tan. We talked before that the tan of x is equal to sine x over cos x. We use that on the unit circle. And the cotan was the reciprocal cos over sine. So those are examples of identities that we've already worked with before. As it said above, sometimes identities can be proved numerically as well as graphically. This first example says determine the non-permissive values in degrees for that equation. Notice it's using the word equation. We don't know that it's an identity yet. But part of this chapter is proving that equations are identities, showing that the two sides are equal for all values of the variable except for where we have non-permissive. And that's what the first part of this question asks us to do. What are the non-permissive values? So if we start by rewriting the equation, our non-permissive values, remember, for any equation, it doesn't matter whether it's a trig equation or some other type, our non-permissive values come whenever the denominator equals 0. So it's important to know what all the denominators are. And so because of that, I would change the secant theta to 1 over cos theta. That's what secant is. Tangent theta, well, I can write that as sine theta over cos theta. Divided by sine theta. Right? The right side was tan over sine. So I got to have a denominator of sine theta there. But then I also remember that tangent is sine over cos. So now when we look at this equation, we see what all of our denominators are. We have a denominator of cosine theta on the left. We also have a denominator of cosine theta on the right, as well as a denominator of sine theta. Those are all of our denominators. And remember that our non-permissive values come wherever the denominator is equal 0. So cos theta cannot equal 0, and sine theta cannot equal 0. So our restrictions on theta are the angles, and it says above there in degrees, where either sine theta or cos theta equals 0. And to help us with that, we can look at our unit circle again. We're going to be looking or concerned with the points on the quadrants, on the axes. These are where either sine or cosine equals 0. Remember that sine is the y value, cosine is the x value. So at 90 degrees and 270 degrees, that's where cosine equals 0. Whereas at 0 degrees and 180 degrees, that's where the sine equals 0. So basically our restrictions here are that theta cannot equal any multiple of 90 degrees. So theta cannot equal 90 n degrees where n is an element of integers. Those are the restrictions on theta. Again, as we back up, see what we did to get there. Your restrictions come where the denominator equals 0. So our first step was to make sure we knew what all our denominators were. We had denominators of cosine and sine. And so neither sine nor cosine can equal 0. And our unit circle tells us where that happens. Every multiple of 90 degrees is where either sine or cosine equals 0. So our restrictions are that theta cannot equal any multiple of 90 degrees. All right, so that was part A. Part B, numerically verify that theta equals 60 as well as pi on 4 are solutions to the equation. Notice that those two angles are not part of our restrictions, right? We said that theta cannot equal any multiple of 90 degrees. Well, these two angles are not multiples of 90 degrees. 60 degrees is one angle, pi on 4, which is 45 degrees, is the other angle, but they're not multiples of 90 degrees. So, for part B, we're going to show that this statement, this equation, is true for both of those angles. The first one being 60 degrees. So we want to show that the secant of 60 degrees is equal to the tangent of 60 degrees over the sine of 60 degrees. So once again, if I do my unit circle, 60 degrees was up there. And remember from the unit circle, the coordinates there are 1/2 comma root 3 over 2. And we also found the tangent to be root 3. And we went sine divided by cos. Let me just draw that a little better. And so remember, this comes from that hand trick, right? You hold your hand out like this, right? This is 0, 30, 45, 60, 90. If you want 60 degrees, you put down that finger. It's the root of this many fingers over 2, comma, the root of this many fingers over 2. Root of 1 or 1 over 2, comma, root 3 over 2. So that's where those numbers come from. Okay? So the secant is 1 over the sine. 1 over the cosine. Secant is 1 over cosine. The cosine is 1/2. So the secant would be 2 over 1, or 2. On the right side, we've got the tangent of 60, which is root 3. divided by the sine of 60, which is root 3 over 2. To divide by a fraction, you multiply by the reciprocal. So instead of dividing by root 3 over 2, you multiply by 2 over root 3, and the root 3's cancel, and you're left with 2. You get the same thing on both sides. So that shows us that 60 degrees is one possible angle that'll make this equation true, to make the two sides equal to each other. But then we also want to do it for pi on 4. So it'll be the secant of pi on 4. That should equal the tangent of pi on 4 over the sine of pi on 4. So pi on 4, that's also on our unit circle, right there. The coordinates there, you might remember, were both root 2 over 2, but you also remember that they actually came from 1 over root 2, which we then rationalize after to get root 2 over 2. The reason I'm writing them like this, though, is because the secant, which is the reciprocal of the cosine, if we write it like the points like that, the cosine is 1 over root 2, so the secant would be root 2 over 1, or just root 2. And on the right side, the tangent, which is sine divided by cos, because they are identical, the tangent was 1, divided by the sine of pi on 4, which is 1 over root 2. And again, to divide by a fraction, you multiply by the reciprocal. And you get root 2. Same thing as what's on the left side. So we've just shown that that equation is true when theta equals 60 degrees as well as pi on 4. Now, remember, the equation is an identity if it is true for all values of theta except for the non-permissive. We've just shown that it's true for two specific values of theta, 60 degrees and pi on 4. We've shown that the two sides are equal. So the equation is an identity for those two angles. But we want to know, is it an identity for all angles except for the non-permissive ones? And one way you can do that is by using your graphing calculator, making sure that the two graphs look the same. So we need to put the two equations into our calculator, the first equation being the left side. Now there is no secant button on our calculator, but remember secant is 1 over cos, so that's what I'll put in y1, 1 divided by cosine of x. One divided by the cosine of x. So that's secant. That's the left side. The right side is tan theta over sine theta, or tan x divided by sine x. I want to be in degrees here. I could be in radians if I wanted to. I've just chosen to be in degrees, which means that when I set up my windows must reflect that. Now we want to show that the equation is probably an identity between negative 360 degrees and positive 360 degrees. So for my x, min, and max, they'll be negative and positive 360 degrees. I'll set my scale at every 90 degrees. For my y values, not really sure what they should be. Let's start by going from negative 10 to positive 10 on the y-axis, and I'll put my scale at 2. Remember, the graph of sine and cos only go up to 1 and down to negative 1. However, the graph of tangent went up to positive infinity and down to negative infinity. So I'm not really sure what my y windows should be, so I've set them between negative 10 and positive 10. So when I hit graph, it's going to graph the two equations, and it happens really fast. On this calculator, it'll show two different colors. And the hope is that it'll be one color directly over the first one. So you got to watch because it happens fast. It'll graph the first one in blue and the second one in a different color right over top of the first one. So it shows that the two equations give us the same graph, which means that they are equal to each other because they give us the same graph, except for where we have non-permissive values. Now, we can see our calculator, even though they don't draw the asymptotes in there, remembering that our scale was every 90 degrees on the x-axis. You can see that you have an asymptote at 90 degrees right there, but then the next one is until 180. So what this definitely shows is that there are restrictions on the variable for theta or x, meaning that it can't be every 180 degrees. But we also said that it's actually, every 90 degrees. Okay, so to check that, go into the trace mode. Notice that it does give us an answer or a value of y when x equals 0. However, that's because we're actually on y1, which is 1 over cosine x. 0 degrees is not a restriction for secant or 1 over cosine, because the cosine of 0 is 1. And so when you find the value of the secant of 0, it's 1 over 1. 1 divided by the cosine of 0, and the cosine of 0 is 1. However, if you use the down or up arrow key, that puts you on the other equation, tan x over sine x, and now you see when you have x equals 0, there is no y value displayed. So 0 degrees is a restriction on the right side of the equation, not the left side, but it's still a restriction on the equation itself. So you can check your non-permissive values as well on your graphing calculator. Okay? So we have shown that this equation is probably an identity. It's an identity between negative 360 and positive 360 because the two graphs are identical. However, it's possible there is some point outside that domain where the two graphs are not the same. You see, you can't put negative infinity to positive infinity in your calculator. You can't. Right? We could play with the windows for x and use something larger, like let's say negative 1,000 to positive 1,000. And now when we hit graph, once again, the second equation is drawn over top the first one for our entire window. But again, it's possible that there is a point somewhere outside that window where the two graphs are not the same. And so this is the reason why choosing specific values for the angle, like we did in part B, to check to see if it's an identity or not, or even using the graphical approach to check whether it is a true identity or not, is not a surefire way of knowing. And we're going to, as we go through this chapter, we're going to see a different way, an algebraic approach to showing that an equation is an identity. For now, we are just checking using specific angles and our graphing calculator. But we have to remember it doesn't prove that the equation is an identity for all values of theta, except for the non-permissive. So we're going to get to that. So this next one, there's a different equation to start with. We have cotan x equaling cos x over sine x. Now that does come from one of our basic identities that we've already used. Remember, tangent was sine over cos. So cotan would be equal to cos over sine. So we already have used this before, and we said it was an identity, but we're going to go through the same processes. First, we'll verify, first we've got to determine the non-permissive values. So we start with cotan x should equal cos x over sine x. And remember, cotan is, it is cos over sine. And this kind of gives us a preview into what we're going to be doing a little bit later in this chapter. Remember I said that there is a way that you can show for sure that an equation is an identity. It involves an algebraic approach. Well, this is what it is. This is a very simple example of that, where you use other identities that you know already. In this case, the fact that cotan actually does equal cos over sine. So you use other identities to show that you get the same expression on both sides. Both sides are the same now. They're both cos over sine. So we've actually jumped ahead a little bit and shown that this equation is an identity for all values of theta, except for the non-permissive ones, which is what we're finding right now. By doing what we've done here, we see that we have denominators on both sides of sine x. Cosine is not a denominator, only sine x is. So our restrictions here are that sine x cannot equal 0. So if we look on our unit circle, let's do it up here because we might have to grab it again. And we put our coordinates on the axes. And also remember that sine is the y value, and the y value equals 0 at 0 degrees as well as 180 degrees. So our restrictions here are that x cannot equal every multiple of 180 degrees. Because in this case, compared to the last one, in this case, only the sine of x can't equal 0. Cosine x equals 0 is not a restriction like it was on the last one. So our restrictions are different. Part B, verify that it is true for those two angles. The first angle being 60 degrees. Nope, sorry, 45 degrees. So on our unit circle, 45 degrees. In the middle, and remember the coordinates there were both 1 over root 2 or root 2 over 2. And so the tangent was 1, therefore the cotangent would also be 1. And that's what the left side becomes. On the right side, it's the cosine of 45, which is 1 over root 2 divided by the sine of 45. You're dividing something by itself, so the answer is 1. We got the same thing on both sides when x was 45 degrees. Now we also want to see the same thing for x being pi on 6 radians. And so at pi on 6, I kind of don't have room on this unit circle up here, so let's just write it. We'll just write it here. At pi on 6, you might remember the coordinates were root 3 over 2 comma a half, and the tangent was 1 over root 3, which we wrote as root 3 over 3 when we rationalized it. But I'm leaving it as 1 over root 3 because the cotan is the reciprocal of that. It'll be root 3 over 1, or just root 3. And on the right side, you'll have the cosine, which is root 3 over 2. Divided by the sine, which is 1/2. To divide by a fraction, you multiply by the reciprocal. And when you do that, the 2's cancel. and you're left with root 3. Same thing as it's on the left side. So we've just shown that this statement is true for those two specific angles. We can use technology to graphically decide whether the equation could be an identity by showing that the two graphs are the same. So the left side will be cotan, which is 1 over the tangent of x. The right side is cos x divided by sine x. So the windows will go from negative 360 to positive 360. And our scale of 90. Not sure what the y windows should be, so I'll just leave them as is. And it happened really fast, but it drew the two graphs, one directly over the other. And you can see that there are asymptotes here. Looks like at every 180 degrees. So if I go into trace, notice that when x is 0, there is no y value given. If I let x equal 180, same thing, no y value given. If I let x equal 90, I get no y value given there either, which doesn't match what we wrote down for non-permissive values. And here's the reason why. We wrote cotan here as cos over sine, but we also could have written it as 1 over tan. Okay? We also could have written cotan as 1 over tan. So if I draw an arrow here, I can also say that's 1 over tan x. And because tangent can be written as both sine over cos, and they'd both be in the denominator, like tangent's in the denominator here, so if you change that to sine and over cos, they will both be in the denominator as well. So because of that, we said that sine x can't equal 0, but now we can also say that cos x also cannot equal 0. And it goes back to the fact that I can write cotan as 1 over tan. So I have a denominator of tan x, which means technically I have denominators of both sine and cos. And that is the reason why our original statement for our restrictions was incorrect. We verified it using the graphing calculator. Saw that there was a problem and then go back and see, well, where does that come from? And I just showed you where. Originally we wrote cotan as cos over sine, but we also could have written it as 1 over tan. So tan's a denominator, which you can write as sine over cos, so both sine and cos are also in a denominator position. So graphing calculator can help us make sure we have the correct non-permissive values. Okay, but the fact that the two graphs are the same tells us that the equation is probably an identity. But once again, we've shown that it's true between negative 360 and positive 360. We can change those x min and max to whatever we want, but we do not have the ability to go from negative infinity to positive infinity. So it's possible there is a place somewhere else outside whatever domain we use to graph. It's possible there is a place somewhere else where the two graphs are not the same. And that's why we use this algebraic approach. And it involves simplifying expressions in many cases. So part A on example 2 says determine the non-permissive value in radians of the variable in that expression. So as you've seen, what we have done in every case is we determine what all the denominators are. So cotan is 1 divided by tan x, all divided by cosecant, which is 1 over sine x times cos x, or cos x over 1. And so, remembering that tan x is sine x over cos x, so because tan x is in the denominator for the top expression, that means sine and cos are also both in the denominator. So neither sine x nor cos x can equal 0, which is also true from this bottom part. The bottom part is 1 over sine x times cos x over 1. They're both in the denominator position as well because they're both under the 1 divided by tan x. We've already dealt with that above here from what's above. Looking at this denominator that I'll circle in a different color doesn't add to our list of non-permissive values. It just is the same as what we had from before, from above. And as we've seen, when this happens, x cannot equal every multiple of 90 degrees. And that comes directly from the unit circle. Now, it does say, though, in radians, doesn't it? So instead of 90 degrees, it'll be pi on 2n. And no degrees because it's radians. Right? So then next it says to simplify this. All right, so this is part B, simplify it. If we start with the original expression, and this is just an expression because there's no equal signs anywhere. Right? So the last few examples we looked at were equations because there were equal signs there. This is not, it's an expression that we are asked to simplify. So we're going to see some different tricks of the trade, if you want, that we'll use to simplify these trig expressions. One of them will involve putting everything in terms of sine and cos. So that's what I'm going to do here. Cotan is cos over sine, and that's divided by cosecant, which is 1 over sine, times cosine, or cosine over 1. So when I write them like that, I can multiply these two parts together here. We're multiplying two fractions, two rational expressions. And to do that, it's top times top, bottom times bottom. And to divide by a fraction, you multiply by the reciprocal. And when you do that, everything actually cancels. You divide top and bottom by cos x, which leaves 1's there. You divide top and bottom by sine x, which leaves 1's there. 1 times 1 over 1 times 1 is 1. So that expression reduces to positive 1, which means if we graph it, you should get the line y equals 1. So let's check that. If you put this equation or that expression into y1, you've got cotan, which I'll write as 1 divided by tan x. I could have just as well done cos x over sine x if I wanted to. But notice I use an extra set of brackets there to keep the numerator together, and that's divided by cosecant x times cos x. So again, I'm going to open up a bracket here to keep my denominator all together. And then the denominator, I'm going to have two factors. So I'm going to do another bracket here for cosecant, which is 1 divided by sine x. Close the bracket on the x, close the bracket on the 1 over sine x. And then that's multiplied by cosine x. Close the bracket on the cosine x and close the bracket on the rational expression. So I've got that all in there, and when I hit graph now, it draws the line y equals 1. If I check my non-permissive value by going into the trace mode, notice that at x equals 0, there is no y value shown. If I let x equal 90 degrees, again, no y value shown. Let x equal 180, no y value shown. Let x equal negative 90 or negative 270, no y value shown. So this confirms that our restrictions are every multiple of 90 degrees. Okay? So on the next page, or on the bottom, I should say, a different expression. We want to determine the non-permissive values in radians for sec x over tan x and then simplify that. So again, to find the restrictions, we write everything with denominators. Secant is 1 over cosine x, and that's divided by tangent, which is sine x over cos x. And so when you look at it like that, it looks like we have only two denominators, and that is cosine x. However, that first expression, 1 over cosine, is divided by all of sine x over cos x. So because of that, not only is cos x a restriction, but also sine x. Because tangent is the denominator, tangent can be written as sine over cos, so both sine and cos are in a denominator position. So neither sine x nor cos x can equal 0. So as we've seen, our restrictions are every 90 degrees, or in this case, every pi on 2 radians. Part B then says to simplify the expression. So secant is 1 over cosine of x, and that's divided by sine x over cos x. So this is the same step that we did above in order to get our non-permissive values. But now we want to simplify this. To divide by a fraction, you multiply by the reciprocal. In this case, when you do that, the cosine x's cancel, and you're left with 1 over sine x. That's what it simplifies. You could write that as cosecant if you wanted to. But we can use our graphing calculator to check this, to make sure that what we started with is equal to what we got up at the end with. Okay, and I did that on the last example. I started with secant over tan. I put that in my calculator, and it gave me y equals 1, which was what the graph gave us, the line y equals 1. This one's going to be different because it's not going to equal 1. It's actually going to equal another trig expression, 1 over sine x. So we'll have to put them both in there. Starting with secant divided by tangent. And secant is 1 divided by cos. Notice I put that in brackets to keep that together. And that's divided by, and I can just write tan of x. And that should equal 1 divided by sine x, because that's the answer I got as a simplified expression. Now in this case, if we're going to check our non-permissive values in radians, our windows should reflect that. Okay, we should go from, let's say, negative 2 pi to positive 2 pi, and a scale of pi on 2. Right? I've chosen to graph this one in terms of radians, which means my mode would need to be in radians as well. Also notice that when you put negative 2 pi into the y or x min, notice that it changed it to a decimal. Same thing with positive 2 pi for the x max. It changed it to a decimal. So all I'm doing now is I'm graphing it in terms of radians instead of degrees. So I have to be in radian mode, and my windows must reflect that. So again, it's going to happen fast. It'll graph the two, one over the other, hopefully, in different colors. So there's the first one, and there goes the second one over it very fast. So that shows that the answer we got for a simplified expression is equal to what we started with. They're the same graph, so they're equivalent. But before we leave this, let's check our non-permissive values. So when x is 0 radians, there is no y value returned. Our next restriction should be pi on 2. So pi divided by 2, no y value returned. Pi, no y value returned. Negative pi on 2, no y value returned. Negative 3 pi on 2, no y value returned. So what I've done is I've just confirmed the non-permissive values are that x cannot equal every multiple of pi on 2. We didn't have to change the two equations because right now I'm on the first equation, which was secant over tan. Had I gone down to the second equation and checked some of these, starting with negative 3 pi on 2, the y value is there. Negative 3 pi on 2 is a restriction on the original equation, not the simplified one. And sometimes that happens, right? And we've seen examples where you have to check both equations to check your restrictions. In this case, our restrictions were checked with the original. Okay? So we use the graphing calculator to confirm that our simplified answer is equal to what we started with, as well as to confirm our non-permissive values. So we've been using the unit circle. And remember, the unit circle is tied to Pythagorean theorem. So from that, we're going to get what's known as the Pythagorean identity. Recall that point P on the terminal arm of an angle theta in standard position has coordinates cos theta, sine theta. Consider a right triangle with a hypotenuse of 1 and legs of cos theta and sine theta. So you can see this right triangle here. To get to this point, you're going to go cos theta to the left, or to the right, I should say. So that is how far to the right you're going, and you're going to go up by sine theta. That gives us that coordinate at P, cos theta, sine theta. And the hypotenuse is 1 because this is a unit circle. And a unit circle has a radius of 1. So if we apply Pythagorean theorem, x squared plus y squared equals 1 squared. X is cosine theta. Sine theta is the y value. And so if you square cosine of theta, it's cosine squared theta. Plus squaring sine theta gives us sine squared theta. This is known as our Pythagorean identity. That sine squared theta plus cos squared theta equals 1. That is known as our Pythagorean identity. It doesn't matter what order those two terms are written in, but this is known as the Pythagorean identity, and we just saw where it comes from. And it is true for all values of theta. Right? There's no denominators there anywhere, so there's no restrictions on theta in this case. And this is on the formula sheet as well. If you look on your formula sheet, you'll see this identity on there. Okay? It is there. So if we look on the next page, it's a different identity. It says, or different equation. Verify that cotan squared x plus 1 is equal to cosec squared x. Verify that that is true when x equals pi on 6. So we've done some of this already. We start with the original expression. And in this case, we're going to let x equal pi on 6 radians. And you remember that cotan squared pi on 6 means the cotan of pi on 6 all squared. That's what it means. So, pi on 6 on our unit circle. Is right there. And remember the coordinates there are root 3 over 2, comma a half. And the tangent was 1 over root 3 or root 3 over 3. And the reason I wrote it as 1 over root 3 is because I need the cotan, which is the reciprocal of tangent. The reciprocal of 1 over root 3 would just be root 3. And again, the cotan squared means that that has to be squared. When you square root 3, you'll get 3 plus 1 is 4. On the right side, it's the cosecant of pi on 6 all squared. The cosecant is the reciprocal of sine. The sine is 1 over 2, so the cosecant will be 2 over 1. That needs to be squared. And you get the same number there as well. So we've just shown that that equation is true when x equals pi on 6 radians. But part B says use quotient identities to express Pythagorean identity, which we just saw on the previous page, as an equivalent identity to cotan squared x plus 1 equals cosecant squared, the one we just worked with. So here's where this comes from. Start with the original Pythagorean identity. And I realize that above it's written as the cos squared x first, sine squared x second, but it doesn't matter. The one that I've written down here is how it's written on the formula sheet. So we're going to see that you can work from this Pythagorean identity to end up with the one that we just worked with above. That cotan squared x plus 1 is equal to cosecant squared x. And to get that, what we do is we divide each term by cos squared x. So sine over cos is, we'll just hang on a second. I think I did that backwards. I should have divided everything by sine squared. Yeah, I apologize. I should have divided everything by sine squared. And when you do that, sine over sine is 1. Cos over sine is cotan. And that must equal 1 over sine squared, which is cosecant squared. 1 plus cotan squared x is the same thing as cotan squared x plus 1. So we've just seen where that equation that we started with above, where it came from. It came from the original Pythagorean identity. And then dividing all of the terms by sine squared x, we ended up with cotan squared x plus 1 equals cosecant squared. That is a variation of the Pythagorean identity, and I think it is on the formula sheet. So let's open up that formula sheet just to confirm that. Oh, I hit the wrong thing. I wanted the formula sheet, not the unit circle. So there we go. So there's the formula sheet. And that's the one that we just worked with. I showed you where it came from. It came from the Pythagorean identity, which is above there. There's the Pythagorean identity that's on the formula sheet. So we took that and we divided all the terms by sine squared theta, and it gave us 1 plus cotan squared theta equals cosecant squared. That's right. We're going to do that next. So that's what the your turn asks us to do. Verify that equation numerically for x equals 3 pi on 4. So part A, starting with this equation, and let x equal 3 pi on 4. So 3 pi on 4. Well, we'll start by using pi on 4, where the coordinates are both 1 over root 2. Or root 2 over 2. Okay. And the tangent was 1, because you're dividing something by itself. So at pi on 4, the sine and cosine are both 1 over root 2. 3 pi on 4 would be in quadrant number 2. And using the cast rule, only the sign is positive there. So at 3 pi on 4, it'll be negative 1 over root 2, comma, positive 1 over root 2, and the tangent would be negative 1. So tangent of 3 pi on 4 is negative 1. So this will be 1 plus negative 1, that is then squared, because tan squared 3 pi on 4 means the tan of 3 pi on 4 squared. Negative 1 all squared is positive 1, plus 1 is 2. On the right side, we have the secant of 3 pi on 4, which is the reciprocal of cosine. The cosine is negative 1 over root 2. The reciprocal of that would be negative root 2 over 1. That needs to be squared because it's secant squared, which also gives us positive 2. So we've shown that that equation is true when x equals 3 pi on 4. Now that we're going to see that it's true for all values of x except for the non-permissive ones, by again starting with the Pythagorean identity, only now we're going to divide every term by cos squared x. Sine over cos is tan. Cos over cos is 1. On the right side, 1 over cos is secant. And that's the same thing as 1 plus tan squared x on the left, equaling sec squared x on the right. So we've just seen where that equation came from, and it's also on the formula sheet. 1 plus tan squared equals secant squared. Right, there it is right there. So now we know where it came from. Right, so we've seen that in, some cases we're going to be doing some simplifying of trig expressions in order to do this. So let's finish off by doing some more questions where we're doing that. There's the 3 forms of the Pythagorean identity above that are on the formula sheet. So obviously you're going to get these for any quiz or test that we have. Okay? And we've seen where they come from. You don't have to memorize, just got to know how and when to use them. So example 4 there says express each as a single trig ratio. Sine over cos. Sine over cos is tangent. That comes from our basic identity. So sine squared over cos squared would be tan squared. and tan squared plus 1, well, from our Pythagorean identity above, that's the third one. 1 plus tan squared theta is equal to sec squared theta. So tan squared x plus 1 will be equal to sec squared x. Now, use our graphing calculator to verify. The two graphs should be the same. The one we started with should be the same as the one we ended up with. So I'm going to have to use some brackets here because I want to keep the sine squared over cos squared together as one expression. But I also need to make sure that the sine of x is all squared. So I'm going to have to open up another bracket where inside that I'm going to go sine of x, close the bracket on the x, close the bracket on the sine x, and square it. So there's sine of x all squared, divided by, open another bracket because I have to square cosine of x. So cosine of x, close the bracket on the x, close the bracket on the cosine of x, square it, and now I'll close the bracket on the original trig expression. But then I also have a plus 1 on the end, right? It's sine squared x over cos squared x plus 1. And that should equal sec squared x, which is 1 over the cosine of x all squared. So these two graphs should be the same. That would tell us that our simplified expression is equal to what we started with. So when I hit graph, it happened fast, but the two graphs are drawn identical, one directly over the other. So we simplified our expression, and we also checked to make sure that our simplified expression was equal to what we started with. So for question B, same thing. We're going to simplify this. Remember I said that one of the tricks to this is putting everything in terms of sine and cos. Cotan can be written as cos x over sine x. And that's multiplied by cos x or cos x over 1. So I've got sine x or sine x over 1 plus, here I'll multiply top times top, bottom times bottom. I'll get cos squared x over sine x. And I'm adding these together. And to add fractions together, in order to add rational expressions, you need a common denominator. And our common denominator here will be sine x. To get that first term to have a denominator of sine x, we need to multiply top and bottom by sine x. And so the top will become sine squared x. Sine x times sine x is sine squared x, plus that second term already had the denominator of sine x, so we don't have to multiply top and bottom by anything, which means the top part stays cos squared x. And what does sine squared x plus cos squared x equal? 1, that's right. From the Pythagorean identity above. Cos squared theta plus sine squared theta equals 1. So sine squared x plus cos squared x equals 1. So this becomes 1 over sine x, which we could also write as cosecant x. But if we're going to check it in our calculator, we have to use 1 over sine x. So let's do that. Let's check it in our calculator. So equation 1 will be the original expression, the sine of x, close the bracket after the x, plus, we don't have a cotan button on our calculator, so I'm going to have to go 1 divided by tan x in brackets. And that's multiplied by cosine of x. Notice I have the 1 over tan x in a set of brackets. Right? And that should equal 1 divided by sine of x. So again, it's going to happen really fast. The two graphs will be drawn over top of each other. This shows that our simplified expression is equal to what we started with because the graphs are the same. This next one, express in terms of sine A and cos A and then write it in simplest form. So 2 tan A. Well, that'll be 2 times sine A over cos A. That 2 is actually 2 over 1. So you're only multiplying the top by 2, not the bottom, because 2 is the same as 2 over 1. And that's divided by 1 plus tan squared A. And if we look above, 1 plus tan squared theta is equal to sec squared theta. So 1 plus tan squared of A is equal to sec squared A. So this will give us 2 sine A over cos A divided by secant squared, which is 1 over cos squared A. Secant is 1 over cos. And to divide by a fraction, you multiply by the reciprocal. To divide by 1 over cos squared A, it's the same as multiplying by the reciprocal. And now we can divide top and bottom by one factor of cosine A, which gives us 2 sine A cos A. There's our simplified expression. In simplest form, which we can check on our graphing calculator. I've got 2 times the tangent of x divided by, and now I'll use brackets to keep this together as a denominator, 1 plus, and I have to do a second set of brackets here so I can square the tangent of x. So close the bracket on the x, close the bracket on the tan of x to square it, and then close the bracket on that entire denominator. And that should be the same graph as 2 sine x cos x. That's what we got for our simplified expression. So when we hit graph, they should be the same graph. Whoa, they're not. So let me check my equations here. Oh, there is. That should have been a bracket. That's why. Here we go. Same graphs. Lohita, do you have a question? Pardon me? Are we good? Okay. If you need a smack upside the head to get you back, let me know. Okay. All right. Any questions on that? So this is going to be a lot of what we're going to be doing in this chapter, where we're going to be proving identities. This is exactly what we're going to be doing. We're going to be using a lot of substitution. We're going to substitute something for something else, which is what we were doing here, right? And one of the hints that we're going to be doing is that if there's no powers anywhere, we're going to put everything in terms of sine and cos, which we've done a lot of. If there are powers, especially squareds, then we're going to be looking to those Pythagorean identities above. So definitely want to have your formula sheet as we go through this section. Sometimes you're going to have to factor in order to make these work. And so a little bit of practice with factoring. This first one, there's a common factor of 3 there that we would start with taking out a common factor of 3. And that expression inside the brackets is a difference of squares because it's a binomial minus sign in between, and both terms are perfect squares. So remember to factor a difference of squares. You take the square root of the first term. The square root of cos 4th theta is cos squared theta. And the square root of sine to the 4th theta is sine squared theta. And then one's a plus, one's a minus. Remember how you factor difference of squares? So right now we have 3 factors. The number 3, cos squared theta plus sine squared theta, cos squared theta minus sine squared theta. What does cos squared theta plus sine squared theta equal? Right. That's from our Pythagorean identity. So it'll be 3 times 1 times cos squared theta minus sine squared theta, which actually is difference of squares again. It'll be cos theta plus sine theta, cos theta minus sine theta. And 3 times 1 is just 3. And you know, there could be definitely an argument to be made saying that by factoring that last step, you actually didn't make it simpler, you made it more complex. And that's fine. But sometimes you need to factor everything just to make sure that you can simplify it as much as possible. So there's your final simplified answer. And if you wanted to do, you could use your graphing calculator to check those to make sure that what we ended up with is the same as what we started with. So 3 times, and then I have to open up a bracket, 3, open up a bracket because I have to go cosine of x to the power 4. Minus 3, and I'll open up a bracket because I have to go sine of x to the power 4. And that should equal 3 bracket cos theta plus sine theta. And then inside the other bracket, cos theta or cos x minus sine x. Right, so these graphs should be the same. And they are. So this just shows that our simplified expression is equivalent to what we started with. Looking at part B, there's a common factor of sine squared theta to take out. Common factor, which gives us 1 plus cotan squared theta inside the bracket. And 1 plus cotan, that should look kind of familiar because if we look above, 1 plus cotan is cosecant. 1 plus cotan squared is the same as cotan squared plus 1. And that is equal to cosecant squared. And cosecant is 1 over sine. And the sine squared thetas cancel, and you're left with 1. So we saw one of this earlier where the simplified expression was 1, so if you graph it, you should get the line y equals 1. So we'll do that just to check. I have to open up a bracket so I can square the sine of x. Plus, open up another bracket so I can square the sine of x again. Times the cotan of x all squared, which again, I'd have to use brackets and go 1 divided by another bracket. Actually, I don't need another bracket because it's just one factor, but I have to make sure that I square it. So I'll clear that second equation. So remember that this whole thing simplified to positive 1. So when I graph it, I should get that line y equals 1, which I do. Right, and this doesn't really talk about any non-permissive values, but we can use our calculator to help us with that, remember. The only denominator we really have here is, well, cotan squared, which is 1 over tan squared. So you have a denominator of tan squared, which means you have sine and cosine both in the denominator. So neither sine nor cos can equal 0, which means x could not equal every multiple of 90 degrees or pi on 2 radians. And I think I'm in radian mode. Yep, I am. So 0 is a non-permissive value. Pi on 2 is a non-permissive. Pi is a non-permissive. These are every multiples of pi on 2. Negative 3 pi on 2. Okay, so you can use the graphing calculator to help us with that. All right, so there's a review of the key ideas that we've talked about, and on the next page there's a trig expression row game. So what this is that for question 1, the answer in column A and column B will be the same when you simplify. You'll get the same simplified expression for column A and column B, number 1. Same thing with number 2. The answer you get in column A and column B will be the same when you simplify. Different than what your answers you got from number 1, but the 2 answers for number 2 will be the same. So really, I mean, that's how you know whether you're doing them right or not. If you get the same thing on the end, at the end, then you should be good. If not, find your mistake. I'll also post these on Google Classroom so you can check. You can see how I did them, but you should try and do them on your own because we're going to be doing a lot of work with this sort of thing, and you're going to be tested on the diploma exam on it as well. And for sure, you want to practice. It's the only way you're going to get good at it is by doing the practice. Okay? So I'll post the solutions to this row game on Google Classroom so that you can check your answers.